8. And just here, I will talk about conservation of mechanical energy. Now, we need to know that, that the term mechanical energy is referring to two types of energy, the potential energy and the kinetic energy. And what does it mean that energy is conserved? That it is, if you choose any 2 points in the your problem, or like the physical, let's say, situation, and you would calculate the energy, then the total mechanical energy at any point equals the total energy at a second point, at a third point, and I will say then the total mechanical energy E is going to be a constant. Now, here we have very special notes for potential energy problem solving. The first thing is that the gravitational potential energy depends on the vertical height above a reference. Okay, that does mean that because for any object, like its mass is going to be constant, G is going to be constant near the surface of the Earth, and I will say the only thing that is variable here, H. And we're going to see later is that expression that we are using for UG is valid even if we are very far from the Earth, or we have high altitudes. Now also I choose here a reference level, and that reference level is gonna be consistent throughout the problem, but you can change it from one place to another. Usually for me, I choose my reference so that my potential energies will be positive instead of having them negative. In the conservation of energy, what is really important here is the change in energy. Then I will say, when we will say EI equals E final, and we will say it is mg, let's say HI plus 1/2 mvi squared equals mg H final plus 1/2 mvi, sorry, this is final again. And I will say I can write my equation in a different way, rearrange it. And from that here, what you can see is that I am looking at changes. Okay, then I'm looking at changes. Change in UG, this is the negative, is gonna be the change in K. What does that mean? This means any decrease in UG is gonna be going to the gain of kinetic. Then I'm interested always in the change in potential energy. Okay, gravitation potential energy is going to be depend only on the vertical position, not on the path taken, and we said that because it is a conservative force. And I will say here, if we go to the book that, like the textbook that we were talking about, I will say mgh should equals minus mv squared. Here we are talking about, I will say the magnitudes, that they should be equal. Now, I will say also here, energy conservation can be a replacement for kinematics problems. I would say kinematics equations and dynamics also. And it's going to be, I will say, a technique that is much easier because now here I deal with, I would say, scalars rather than using vectors. Here, just this is one of the situations where we also can say we use also diagrams to show changes in energy. Then I will say here, if we have that, or let's say stone or whatever, it is at y equals 3 meters, then, and it is at rest, then all what I have is potential energy. Then here, like the energy buckets, we call them, or sometimes we use what is called like energy bar diagrams. Then energy bar diagrams, you know, you are familiar, I believe, with like bar diagrams. And here we are dealing with, let's say that my bar diagram, or all my energy is just I would say gravitational potential energy. I will show you here when y equals, we said like 3 meters, and v equals 0. What I can say here is like the bar diagrams, and here I will plot E. This is gonna give you an indication of like how much K I have. Okay, because V, it has to do with kinetic, and this one is with UG. And when I am at that, let's say, altitude, okay, then all this is UG, and according to what I have for the velocity, this is 0. And then when I add these two, I'm gonna get this. And you can say here that E equals UG because K is 0. Okay, when that object is gonna reach somewhere in the middle where, or maybe it's not exactly in the middle, it's like any point here, then I will have that UG, it's gonna be only 1/3. Then the 2/3, they will be what? A kinetic, so that now I will have also again the same, like 3 of these is gonna be like, this is my E. And finally, when I will reach my reference, which is my floor here, remember E is gonna be constant throughout all, and then I will have my kinetic is gonna be the maximum, and for my UG is gonna be 0. Then these are called energy bar diagrams. Okay, and then what we have here is that I will say energy, and when we say conservation of energy, we say that energy cannot be destroyed and cannot be created, but it can be converted from one form to another, as we can see here, or it can be transferred from one object to another. Now, one of the most also important things that we need to pay attention to is the equation that we are using for potential energies and kinetic energy. And for example, here, if we are talking about a roller coaster where we don't have any friction, then I will say the speed of a roller coaster would depend only on the height compared to its starting height. Then I will say, like here, if I will choose my reference at this point, UG equals 0, then I have this much of like UG, and then here I have decreased my UG to 0, then all what I have is kinetic. And here I will have portion of the UG, and the rest is gonna be kinetic. Now, for conservation of energy, we need to draw a picture. Pictures, they're gonna be very good in, in visualizing the what's going on. Also, I will determine the system for which energy will be conserved. And here, remember, I said system, which means it is more than one object. and usually 2. Okay, and then also I need to decide where is my initial and my final and figure out what I am looking for, apply conservation of energy, and then solve for what I am talking about. Here, for example, I'm showing you one of the examples that we have, assuming that the height of the hill is like 40 meters and the roller coaster car starts from rest at the top. Calculate the speed of the roller coaster car at the bottom of the hill and at what height it will have half of its speed. And they said take y0 equal y equals 0 at the bottom of the hill. This is not always is going to be the case where we're going to tell you where to choose it, but I will say it is recommended that you use the lowest point. This is what I'm doing usually. For me, I consider the diagram that I have is my diagram. And also I have labeled my distances. I said where is my I, where is my final. And the most important part here is where my UG equals 0. I like to use charts here or tables. Then I'm going to say I final, and this is UG in joules, and this is kinetic energy in joules. I know at the initial here, I have mgyi is going to be all my, gravitational potential energy. And when it will reach finally, my final position here is going to be 0 because it hit my reference. Now, it was also mentioned in the problem that it is from rest, then my kinetic energy was initially 0, and then finally is going to be 1/2 mv final squared. Okay, I know I can apply EI equals E final, then I will say mgyi equals 1/2 mv final squared. And here you can see that I have crossed out the mass from the two equations. This is not going to be the case always. The reason is sometimes when we go to having like non-conservative forces, you might have terms that they don't have that mass, and then, or like if I have a spring in my problem, that mass will not cancel. Then don't make it a habit that and if you will find like this question without having a mass, don't panic. It is just because the mass will drop. Okay, then finally I will be able to calculate what is my V final squared, and then I will get my V final. Now, they want us to calculate at what height it will have half of this speed. Half of this speed is going to be 14. Then I know that EI is 1/2 mv final squared, and then I can use this one, or I can use here mgyi equal 1/2 mv squared plus mgy, and that y is going to be any height that I wish to calculate, and then I will be able to calculate that this y, it is at 30 meters, where my object is going to be 30 meters, is going to be the speed is going to be half of the initial speed. Okay, this is here about a jump, a film of Jesse Owens' famous long jump in 1936 Olympics shows that his center of mass rose 1.1 meter from launch point to the top of the arc. What minimum speed did he need at launch if he was traveling at 6.5 meters per second? This one is going to be, okay, like here I have my athlete here is jumping, okay, to this is like 1.1 meters, and um, you know, and at that moment he has a speed of 65 meters per second, and I'm looking to find what is going to be the highest, what minimum speed did he need at the launching so that he will be able to get that velocity and that height. And of course, okay, here we know that the initial UG was 0, and then it will go to that height, which is the MGY final. And initially we have that 1/2 MV 0 squared, and then he will reach 1/2 MV final squared. I will say EI equals E final, and I can rearrange and then calculate my velocity to be 8 meters per second. I'm gonna stop here for this also, and I will have a third recording